Hi, and welcome to the live stream. My name's Andy, and what do we got? We got 5 people watching, so all 6 of us we're gonna cram into CTJ here, and in about 2 hours, so 9 o'clock, 9 o'clock Eastern time, we're going to depart, and we will do some planning here and see what it is we're gonna do in the meantime. The cat is already eager to start planning. So we will peel the cat off the map and take a look at where we're going. So, like I say, we're gonna go Owen Sound to Waterloo in about 2 hours. So we'll look at current weather. We'll look at the routing and what we think about the route, different considerations, and how we want to get into Waterloo and that sort of thing. And yeah, we'll start planning. So just stand by for peeling the cat off the map. Kitty. Okay. So here we go. I will throw the chat up in the corner just in case. Bam. So welcome everybody. Here is paper. What's this? Still using paper? Yeah. So on the transport written test, the standard is still paper maps, and that's what you'll be using on the actual test. They do give you like a laminated one, and then you'll do like dry erase markers on it and that sort of thing. Is currently what they're doing. But yeah, it's paper and then some math and that sort of thing. So we're gonna start with the map first, and we're gonna look at what we're doing on there. And then after we do some drawing on the map and kind of get an idea of the route. Hey Devin, how's it going? After we get an idea of the route, we're gonna move over to this navlog template, which is in the description below. If you want to follow along, quickly open that up and hit Control P or whatever, print it off, and you got this to follow along. Otherwise, no big deal. You don't have to fill it out with me, but just keep an eye on what's going on. And we'll also look at kind of ForeFlight later and how that compares to the numbers that we get on paper, and go from there. So kitties on the map. Okay, so the first thing I want to look at is just kind of the route. And what I find is this is a little bit different than the test question. On a test question, they're going to tell you, okay, this is your route. You're going to go from this point to this point, and this is exactly how you're going to plan it. And you're going to overhead this set heading point or whatever. They're going to be very specific on the written test because they want everyone to plan the same route. But when we are doing actual nav planning in the real world, oftentimes more of the planning, more of the actual things that are going to keep you safe, and the things that are going to make it so you don't have unexpected challenges, most of that planning happens in your head, and it happens by actually just looking at the map and seeing what lays along my route. What's the terrain doing? Do I have obstacles? Do I have airspace I shouldn't be in? Are there any hazards? Like gliders and that kind of thing. So that's where I want to start. Is just I'm not going to put any lines on the map. Is just kind of scrolling around the map and seeing kind of what's out there. I think that's an underutilized strategy for kind of navigation stuff. So, whoops, to do that, I'm gonna cheat. I'm gonna right away skip over to ForeFlight here, just so that it's a little bit easier for you guys to see me zoom around the map here. So, looking at, hang on, I'm trying to rotate it. Won't rotate, that's fine. So, here we are here in Owen Sound. This is where we're going to depart, and we are headed to Kitchener-Waterloo down here. Along the way, let me just draw, and this isn't the route that I want to fly, but it's just easy to draw in something quick. I'm just going to draw a straight line from here to there and kind of get an idea left or right of my line and kind of what's in between. So we've got you know, the Kitchener zone there, obviously. It's a controlled airport. We've got some various lakes and stuff on the way in. We've got, you know, these little towns of Fergus and Elora and that kind of thing. As far as hazards, there's a couple, you know, like glider clubs. There's this little blasting area over here. I think that blasting area won't be a factor for us in the direction we're coming from. We would probably be high enough that it's not a factor, but something to bear in mind. We'll look at that as we start drawing our lines. A couple little grass strips and stuff around, and really that's about it. There's not much for like hazards, I guess. One obstacle to think about, we've got this big wind turbine farm here, so that's also going to be close to our route, even though this won't be exactly our route. So those are the sorts of things to look for there. There's no things like restricted airspace. There's no big open bodies of water that we're going to fly over. Stuff like that would be things to look out for. You know, if we were going somewhere like Parry Sound, we wouldn't want to go right across the middle, of course. We would want to go around. You know, we've got the Meaford base nearby, but we're going the opposite direction. So those sorts of things. That's where I like to start, is just, you know, assess kind of any major hazards and really anything that's going to define our route. It would suck to draw all the lines and get halfway down the math and you realize, oh, there's a restricted airspace right in the middle. So that all seems fine. Okay, and what I think is, I don't like this kind of direct straight line for the sake of this planning, especially if you're not that current and you want to you know, practice navigation. We should use a set heading point, something that, and we'll see when we look at the math here in a minute. But it makes the math a little bit simpler, and then also it allows us a really accurate point to fly over, so that we know that our math is accurate from the moment we leave. Otherwise, you're like, oh, am I? Did I turn? Am I left or right on my route? Imagine we take off runway 36 and we depart out to the north, of course, and then we do like a left turn out over this way. Well, already we're off track. We're out over near the city over here, and we haven't even started. We're already about 3 or 4 miles off track. So instead of doing that, we make a set heading point so that we start on that point and we can fly a straight line the whole way. Okay, so that's what we'll do. And let me switch to the map. So what I'm thinking for a set heading point, so here's the Owen Sound Airport here. Let me turn this way for now. Okay, so we've got Owen Sound here up at the top, and this is north up at this moment. And then here is the town of Chatsworth right here. So there I think Chatsworth makes a really good set heading point, because it's maybe a little bit out of the way. It's slightly to the west, but you notice there, especially on a 36 departure, it's not that far out of the way, because we're probably going to kind of want to come off of runway 36 and then turn and end up over probably pretty close to the city, or, you know, between the airport and the city. So it's really, if we're starting from here going along to Chatsworth, no big deal. So we'll maybe set off with that. So set heading over Chatsworth. So with that in mind, we kind of have 2 legs. We're going to be Owen Sound to Chatsworth, and then Chatsworth down to Kitchener, down here. So that's the plan. So I'm going to start with those lines first. That'll be my first step. Okay, so we got Owen Sound up here, and we have Waterloo down here. So I'm going to start with the lines. I'm going to use a straight edge, of course. And one thing to bear in mind, especially on the live stream on camera, if I used a pencil to draw this line, you're never going to see it. Well, it's the same thing in the airplane, right? Looking at how ForeFlight represents it, look, the line is not, it's not like a thin, dark, black line. It's this bright magenta, like, hey, by the way, here's where you're going. So I want to replicate that. I got my magenta, well, it's pink, but I got my pink highlighter in order to make a really clear line. because I want to make sure that it's visible. Visible when I'm in flight, bouncing around in the turbulence and that kind of thing. So I'm going to start, Chatsworth is way up here, and then I have Kitchener down here. So I'm going to put my straight edge on there and draw as straight of a line as I can, and as accurate a line as I can. I want to go from the center of the airport to the town of Chatsworth. We're obviously not taking off in Chatsworth, that's our set heading point, but if you were taking off from an airport and going direct, you'd want to be from the center of the airport to the center of the airport, so that's important. Nice thing about doing this with a highlighter as well is you can see the details below it. So the highlighter doesn't actually block anything from being readable and that kind of thing, because along the way we've got all kinds of little labels from various different towers, or like this blasting area here. So that's an interesting point. Take a look at, I will do the good old paper manual zoom in on my blasting area here. So here's this this blasting area. You can see it is offset from my line. My line, if we are on the line, it won't go right over this blasting area, so that's good. And as we are in flight and navigating, it would be helpful to just visually confirm that yes, we're not going over that blasting area. But like I say, we're probably high enough that it's not significant, but it is just nice to know that we're not right on it as we go by. Cool. So other than that, I will also put in the line from Chatsworth to the, or rather from the Owen Sound Airport to Chatsworth. Bam. So we take off Owen Sound, visually navigate to Chatsworth there. We will do like a heading and stuff like that for calculation anyway, but it's really just going to be visually fly there, and then we'll set heading and we'll be en route. On the way into Waterloo, be interesting to look at. Let me just switch to the ForeFlight just because it's hard to read what we're looking at. Stand by. So I put my my leg in there. So as we look at on the way into Waterloo, we do have some nice towns nearby. We've got the town of Elora that will go right by. We got this little town of Alma. We got this big town of Elmira that we might see in the distance. So those are good too, because as we get closer to Waterloo, they're going to really want to know where we are, so that, or we're going to want to know where we are so we can tell them where we are, so that they can find us, so that we can get in and land at a controlled airport like this. So that's all good. We got some nice landmarks along the way there. About the halfway point, or a little bit, I guess the 2/3 way down, we've got Luther Lake here that will be flying by. Yeah, so we're how much height for a blasting area? That's an interesting question, and I don't know that there is an answer. If there is, I would love to know, but I've never seen anyone's site like be this high, and the reason being is it's more or less just highlighted on the map as like, here is a potential hazard. I would hazard a guess that that they're not going to go, like, the blasting probably isn't going to be that dangerous above even a few 100 feet, but you don't want to rely on that, right? Think about what they're doing. They're probably using dynamite to blow up rocks and, you know, turn it into gravel or whatever so they can scoop it out, or something like that, right? So there's gonna, like, the risk would be tiny little fragments that are able to go very high. Even with that, I think a very tiny fragment wouldn't go more than a few thousand feet. So here, I'm planning on being at least a few thousand feet. So we're at definitely the upper end of when I would consider it a hazard anymore. And in our case, we're not going to go right over the blasting area, So the mix of those two things, I would say, yeah, we're pretty safe for this route. But yeah, it's definitely something to something to consider for sure. If I got if my route was right over top, maybe I get pushed down due to weather, and maybe I'm only at 2,000 feet or something like that. Now I might start to get concerned. I don't know if they're blasting. They don't put out notices or anything like that. So yeah, great question. So okay, here we go. We got our lines on the map. One thing that you'll hear a lot about, and I think that there's there's lots of different opinions about this topic, is the idea of, do I need the 10-degree drift lines on the map? And the answer is whatever you think. On the written test, they will likely ask you questions that might be made very slightly simpler with the 10-degree drift lines, but I would say that I don't recall seeing many questions that were like, you need to draw the 10-degree drift lines in order to solve this question. I don't think it's that absolute, but a lot of people recommend the 10-degree drift lines. And the reason why they recommend the 10-degree drift lines is it can be a little bit simpler for if you are, say, over like barren landscape. So let's say, for example, we're not navigating here in southern Ontario, but if we're up north, kind of, here's Sudbury here. Out in this area is pretty barren, not much going on. You start heading east into kind of Quebec, and especially northern Quebec. There's just lakes and trees. And so in these sorts of scenarios, some of your navigation decisions might be based on math once you get en route. Maybe you identify you're over a specific point, and you're not going to be able to identify another specific point for 10 miles. Well, in that sort of scenario, 10-degree drift lines on the map could help you a little bit, because then you can see at a glance, I am 3 degrees off, and how to correct for that. So let me just show that part. I'm not going to do the drift lines for my my set heading leg, because I don't think it's required, but I will do the drift lines in a different color. Very important. I'll come back to that. I'll do the drift lines for my main leg. So in order to do that, I'm going to use my fancy square protractor, and I'm going to set it on the first point. So I'm going to set it on Chatsworth here. I'm going to put the very center of the protractor on Chatsworth. This is a very odd way to measure angles. You don't normally do it this way for headings and stuff, but for the 10-degree drift lines, I'll do it this way. I'm just looking to make sure I got it the right way around. Okay, so I've got my dot exactly on Chatsworth, and I've got north is lined up with my line. And what this 10-degree drift line is measuring a difference. It's a difference between my desired track and 10 degrees off of it, to the left or to the right. So that's what we're measuring. So what I'm going to do is I'm just going to make a little mark 10 degrees this way, and I'll make a little mark 10 degrees this way. Okay, so I got 2 little marks. You might, oh yeah, you can see those pretty good on camera. And then I will take the ruler, and I will extend a line now from Chatsworth through that line, and then out at least beyond the halfway point on my route. Something like that, and the other side. And some of you are probably thinking now, like, he's using a pen. He's using a pen on the map. Oh my God, I can't erase it. What if I make a mistake? And that's a good point. You may want to do this in pencil first, but I highly recommend, when you actually move to the airplane and you're going to do it in flight, if you're pretty sure that this is the way you want your map set up, go over it in pen. And the reason I suggest that is pencil's very hard to read on the map, right? Same thing why I say, okay, do like a highlighted line, something really visible for the main route. I would say equally important, make the 10-degree drift lines very visible, because you need to be able to see them. And like I say, you need to be able to differentiate between the two. It's very easy. Won't admit that I've done it, but it's very easy to start out en route along a 10-degree drift line thinking that that's your track, and then you get 10 miles down and you go, I don't remember crossing over that town in my planning. Oh, right, that's a 10-degree drift line, right? So definitely make them in at least a different color. Okay, and I will do the same thing 10 degrees out from the destination. I'll do the same thing. Keep track of where you drew your line. Oh, found it. Okay, so I will hold it up so you can kind of see. Finding, there we go. Okay, so you can see here's Waterloo, and then you can see the 10-degree black lines splaying out from it, and then we've got our pink main line. And then somewhere around the middle of the route, I'm just going to turn this sideways so it's easier to see. Around the middle of the route, you're going to get where the 10-degree drift lines intersect like this. You can see that there where the lines come together here and up here. So you got the 10-degree line coming out this way, and it intersects with this one going to the destination there. So that is going to be right at the halfway point, because if both of them were 10 degrees, right across here should be about halfway. I'm also just because I may be off very slightly, if I measured maybe 11 degrees and 10 and a half degrees or whatever, I might be slightly off. So I will also measure the distance and do a halfway mark as well. That again is also optional, right? I was saying that the 10-degree lines, if you think it's helpful, put the 10-degree lines on. If you think it's helpful to have a halfway and a quarter and a three-quarter waypoint, put those on. Maybe that's not as interesting. Maybe you want every 10 miles of distance, put that on. It is kind of individual that way in terms of what makes the most sense in your brain when you actually get out en route. Yeah, erasable pens. Yeah, so I was going to mention that. I'm doing the totally permanent, totally get it right on the first try method. So I hope I don't screw it up. But this is not an erasable highlighter. There's erasable highlighters and then erasable pens that are great. I haven't found much for, like, it would almost be better to do like with sometimes I want a really dark line like an erasable Sharpie, but I don't think that exists. But yeah, definitely these highlighters, because they're very brightly colored, can be good. We have some that we use that are erasable at the flight school there. So cool. Okay, so I think that's about it for preparing the map, and then we're gonna have to go to the navlog to see what else we need to add. So the navlog, I'm gonna start adding into here. I'm gonna start by saying, okay, my kind of climb to Chatsworth leg, right? Okay, that doesn't fit in there. I'll say 2 Chatsworth. This leg, we're going to be climbing probably most of it, and we'll get into calculating that. Actually, we should calculate that at the end, because there's a couple different ways to think about that. We will calculate the second leg, oddly enough, first, because that's the one that's going to define what we do on the first leg, right? So we're going to be climbing to an altitude. Well, what altitude and that kind of thing. So let's actually start with calculating the second leg. So we're going Chatsworth to CYKF here. Okay. And first things first, it's asking me for the MEF. So the MEF. MEF stands for maximum elevation figure. And you can find out about any of those acronyms because it says look at the map. If you're not sure and it's on the map, it's going to be in the legend. So you can look into the legend, lining up upside down on the camera. Where is it? It is right there. Oh, there we go. Next to this 38 here, there's some text that you won't be able to see on the camera, but when you read your map, it will talk about it, and it says the maximum elevation figure, MEF, is depicted in thousands and hundreds of feet above sea level. So that's the MEF that it's talking about on our nav log. So we need to determine the MEF for the route. So like we're seeing on the legend, the MEF is these larger numbers and their altitudes in above sea level. And there is a bunch of them around our route. There's one here, there's one here, there's one over here, there's another one way over here on the east side. Our route is over here, of course. There's even some south of Kitchener and all that. So there's a bunch of MEFs. The MEF refers to the quadrants. Let me get to a space of kind of like open water down here, like over the middle of Lake Ontario. It's easier to see these quadrants. So you can see the grid lines here from the graticule, the latitude longitude lines. So the latitude longitude lines, every 30 minutes of latitude or longitude, it makes this this grid pattern. That's what those MEF numbers are referring to, is the maximum elevation within that latitude longitude grid. So that's what it's talking about. So we need to really assess which grids during our route are we going through, and it's probably easier for us to assess that here because we can zoom in more. So you can see we start off in Owen Sound in this block, and that block is 1800. And then by the time we get to Chatsworth, we're going to be in this block. That block is 2100. Then we fly down into this one. That's 2000. We fly across into this one. That's 2200. And then we're in this one that Waterloo's in, which is 2100. So we fly through all those blocks, our flight path does. And the highest of them was this one, this 2200 feet here, that's just north of Waterloo. So that is our MEF. That is our maximum elevation figure. So we can put that right in, 2200. We did see on our climb to Chatsworth, though. Oh, there we go. Yeah, 2200 in there. We did see on our climb to Chatsworth that the block up here was a different altitude. It was 1800 on our initial climb, but by the time we get to Chatsworth again, we're into this block. So our MEF on that Chatsworth leg is a little bit lower at 2100, but pretty close to the same. Okay, I keep hitting 0, which is changing things, and I should stop it. Okay, so yeah, so that's our MEF 2200 here. Can I fly at 2200? Do I want to fly at 2200? What does it mean to be 2200? What is this maximum elevation figure? Does it imply, kind of where we can fly, or or rather how high we are legally allowed to fly or can safely fly. What is it really talking about? So there's a bit of nuance to that question. If we're in the Owen Sound area doing a local flight, we fly at actually 2,000 feet quite often. And that's only 200 feet above the MEF. So the circuit height is only at 2,000 feet. So clearly it's not like the ground is at 1,800 because we wouldn't be doing that. What the MEF is saying is this is the highest obstacle in that quadrant, and they round it up, pretty conservatively to the nearest 100. So 1,800 feet in the Owen Sound area is the highest obstacle, and there's one down here which is 1,600. That one's pretty high. I think there might be another one up over here. No, that one's not that high. I'm pretty sure that 1,600 is one of the highest in this area. Oh, there's one right there, 1,757. So that'll be the obstacle. It's actually slightly outside of the quadrant, so they've given us a little bit of a wiggle room, so that's nice of them. So that 1,800 is just saying that there is an obstacle that is up to that height. If we're going to go below 1,800, for example, we go below 1,800 all the time when we're landing at 1,008 feet above sea level, you just really got to know what the obstacles are going to be, right? I would also say I wouldn't linger at 1,800, especially for longer distance cross-country stuff, because you're not going to be able to constantly assess obstacles the whole way, or at least you could, but it would be a lot of work. So basically, they're saying stay above 1,800 if possible, and that will keep you clear of obstacles. It's nice for a longer cross-country like this, give ourselves a bit of a buffer, and that's where this next cell comes in, this mocha, and it actually says right on the form here, plus 500. So I'm going to take my 2,200, and I'm going to make that 2,700. And that will be a good mocha for us en route. We should be at least 2,700 feet in the en route phases. Okay, so that brings in the next question. What altitude should we fly? What altitude can we fly? Well, to answer that, you got to know about the cruising altitude orders. And looking at that, the cruising altitude orders have to do with east or west headings, right? If we're going an easterly heading, then we would, or rather an easterly track, it's actually the direction your airplane's moving over the ground, not the heading that you're flying. If you're on an easterly track, you should be odd thousands plus 500 feet for VFR airplanes. If you're on a westerly track, you should be even thousands plus 500. The latitude longitude lines are based on true, it's not based on magnetic. The cruising altitude orders is based on magnetic. So you can see here, here's this 10 degree the 10 degree variation line here. So we know that the magnetic is 10 degrees off of the true track. The meridian right beside it, the longitude line here, is the true north, right? So looking at our line versus that true north, without even pulling out a protractor, without doing the math and adding the 10 degrees and being all fancy with it, I can see that's more than 10 degrees, right? It's at least something more than 10 degrees. Maybe it's like 20 degrees off of north-south. So I'm pretty sure our route is going to be taking us on a westerly magnetic track. And so what that means for us is we should be on an odd 1,000 plus 500 if we're going to be following those cruising altitude orders. So that's the plan. So I would say, given that our minimum is 2,700, why don't we go 3,500? Bam. There we go. You could go higher. We'll look into some of the weather here. There was some clouds that were in kind of the 4,000 above ground level before. So I'm thinking kind of 3,500. We could do 5,500 as well. That would also work. But let's just go with this for now. Some things that might change your decision on that. Let me just look at some weather actually before we commit too heavy to it. So, oh, there we go. So yeah, we had some few clouds at 4,000. It actually cleared right up to sky clear. So that's interesting. Other things that might affect your decision is the winds. So this is the upper level winds out of Wyerton here. And so we can see the 3,000 foot winds. What time is it? We are at just after 23 Zulu. Oh, and you can look at the bottom of the page here. So we're just after 23 Zulu. It'll be 25 Zulu when we're planning to take off. So up here, that would be into this middle block here. So the winds at 3,000 feet are 350 degrees. At 6,000 feet at 060 degrees. 5 knots up to 8 knots. Pretty similar winds. So I don't see a wind advantage to go higher. One advantage that you could have to go higher is it's easier to navigate a lot of the times. Yeah, we're gonna be doing a slightly easterly. It is, mostly south, but slightly east. So kind of a 350. Actually, this should be more of a, like, just my guesstimate, not actually doing the math yet. Should be more of a tailwind at 3,000 than it is at 6,000 because we're going slightly easterly, mostly south, but southeast. Whereas this is slightly northwest, so that should be pushing us along our route. So if anything, yeah, probably the 3,000. I haven't calculated it out, but we'll probably gain a few knots just to be down at 3,500. So that's reason enough for me. That's kind of what I was thinking, was 3,500. Okay, next up, outside air temperature. This one's a tricky one down at 3,500 because on this upper level wind chart, they give us the temperature up higher, but they don't really give us one at 3,000. So what we can do is we can look at Wyerton. Wyerton is 700 feet above sea level. So let's round it down. Let's call it 500 feet above sea level. Ooh, we're being edgy. So we're calling Wyerton 500 feet above sea level for the sake of this temperature calculation. Their temperature is 26 degrees Celsius. So we need to be 3,000 feet above that. Temperature changes 2 degrees for every 1,000 feet. So 2 degrees for every 1,000 feet times the 3,000 feet that we're going, that's 6 degrees. So our outside air temperature at 3,500 feet should be about 20 degrees Celsius right now. That makes sense too because they're saying, oh, about 15 degrees Celsius at 6,000. So that seems like we're in the right ballpark. So I'll put that down. So 20 degrees Celsius outside air temperature. Okay, pressure altitude is next. Pressure altitude, I'm going to do it based on Wyerton as well, because by the time we get to Waterloo, it might change down there. But I will just compare them right now to see how similar they are. So Wyerton has an altimeter setting 29.96. I will zoom in very slightly. 29.96 out of Wyerton right now. And Kitchener, 2993. So it's pretty close between Wyerton and Kitchener. So I'm okay with that. I will just use Wyerton for the whole leg. That will be fine. So 2996 out of Wyerton. Gonna have to do a little bit of math. So we got 2996. We're gonna subtract that from 29.92. And when we do that, we're gonna get 0.04, and that's a negative number, and that is not actually 4 feet. That would be 40 feet. So 40 feet lower than expected. I would honestly, for the sake of this kind of thing, I would probably just throw that out for any of the charts that we're going to put in. But just to show that we calculated it, I will put that in there. So we are normally 1,008. So we'll call it, what is that? That is 920. Hang on. I'm going to be lazy. I'm going to pull out a calculator. Minus, yeah, 968. 968 is our pressure altitude, but like I say, it's so close to 1,000 that, you know, if you're going to pull out any performance charts or anything like that, I would just use 1,000 because it's very, very close. Okay, density altitude. Density altitude, remember how to do this one? One's a fun one. Everyone likes density altitude. Density altitude with the E6B. So you've got a couple different windows to look at on the E6B. We have the altitude correction window and the airspeed correction window. Oddly enough, density altitude is on the airspeed correction window. And I think it mentions, does it say that on here? Yeah, it does on mine in the description down here. It does mention density altitude and refers to this little line here. So we will punch this in. Okay, so I got my E6B. We have a pressure altitude of 968. We know that, call it 1,000. And the outside air temperature we calculated was 20 degrees Celsius. So I'm going to take those and I'm going to line them up in this little window here. And this is very tricky because it's very easy to get the scales backwards. It's very easy to people have all kinds of trouble with these windows. So let me go over here so I can point better. So what I want to look for is the pressure altitude, of course, on this scale, and then the temperature, of course, on this scale. But take a look at this. This is negative 50 degrees, and then it's positive going that way. So the more left you go, the more positive you go, which is very strange, and that always messes with people's brains. So be very careful with this scale. The other thing is, it's from negative 50 degrees Celsius to positive 50 degrees Celsius. That's a huge scale, and so it's not very precise doing this calculation to begin with. Okay, so we know we're approximately 1,000 feet, so I want to take that point and solidify it in my brain. I don't want to lose that point. We're at 1,000 feet pressure altitude, and we're at plus 20, so that is going to be, I got to get my hands in the right spot, 1,000 feet plus 10 plus 20. I got to line those two up with each other. That's what I'm going to do. I got to do that. Okay, now that I've done it, I want to make sure I did it right because it's very easy to skip one or something. So again, I'm going to start with the pressure altitude scale. We know we have 1,000 foot pressure altitude, so that's 0. Camera angle, there we go. That's 1,000 right there. So that's the point that I'm looking at. And then we have 0 degrees, we got 10 degrees, there's 20 degrees. So those two are lined up. If I was to continue, I'll go 30, 40, 50. So that makes sense. I got the scale right as well, which is very important. I'm going to zoom in even more and use my telescoping eyes. Yeah, it looks pretty good. It's lined up pretty good. Okay, so I got those two scales lined up. Now, my E6B here might be slightly different than yours is. I'm going to zoom to the real E6B for just a moment to show that normally when you line these up, you're looking at this little density altitude here. So I'll do it again. I've got pressure altitude. Okay, I believe that's lined up there. So I've lined up my 1,000 feet with my 20 degrees here. Most of them have the density altitude inside here, and you're looking at that arrow there. Just on the software I've got, they've broken it out as a separate thing here. Oh, did I move that? No, I didn't move it. They've broken it out as a separate thing. So it looks like it's just under 1,000 foot pressure altitude. So it doesn't really do us any help for an exact number, but if I was to guess, I'd maybe say that's 1,800 feet. So I can put that into here. Oops. Swapping back and forth. There we go. So I got 1,800 feet density altitude there. What does that mean? Well, that means when we're flying. Oh, I just realized what I did. I did this based on the based on the airport elevation. Oh, that was silly of me. Okay, I'll quickly redo that, but that's an interesting one to know. And you would do this calculation actually likely as you know, part of your performance as well. For your departure airport, you would do a density altitude calculation. So when we're taking off out of Owen Sound, the airplane feels like it's at 1,800 feet, which is good to know. 1,800 feet, no big deal. The airplane can handle that fine. We fly at 1,800 feet all the time. But if that number said like 8,000, okay, well, maybe we got to really be careful about our takeoff performance charts and really look at those more carefully. I will put this in the climbing leg. It's probably not that far off from what we would do there. Okay, so let's look at then again. We know we had a 40 foot correction there, so it's not going to be 3,500 foot altitude. We're actually going to be 2460. Oops, 2460. Or sorry, no, it's 3460. Yeah, it's only a 40 foot. 3460 is our pressure altitude. Good reason to come back to here and do another one. I will do it on the iPad so you guys don't have to sit through that and you can see it. Okay, so this one, we're a little bit higher. We're going to be basically, again, call it 3,500. It's close enough. 3,500 and the 20 Celsius is actually what we'll be doing here. So we have, again, let me zoom my face over there. Whoop. Okay, so that was 1,000, 2,000, 3,000, kind of halfway in between for 3,460. So this is where we'll be here. And then we'll be looking at, again, way up over here for my 20 degrees Celsius, way up here. So let me zoom this across. Oh, I started at 5. Hang on. There we go. 1, 2, 35. There we go. That's why it's not lining up. And 20 degrees Celsius. So I'm going to line these guys up together. Right about there. Okay, and I will confirm again. So we start 0, 1, 2, 3, 3,500 feet right here. And then 0 degrees, 10, 20 degrees. So they're lined up there. Okay, so now we're ready to look at the cruising density altitude. And that's quite a bit higher of a number. We've got just about, we'll call it 5,000 feet. So that's interesting to know. The density altitude is probably a little bit higher than the 1,800 feet back here at the ground when you factor in the temperature there. So let me go back here. Okay, so we actually have about 5,000 foot density altitude there. So that's good to know. So airplane feels like it's quite a bit higher, and that makes sense. It's quite warm outside there. So cool. Okay. From there, we've got our density altitude. We're going to start dealing with some of the performance numbers and that sort of thing. One thing to bear in mind is when you are doing this nav log, if you knew, a few days before that you're going to do this trip, you might fill in some of these numbers well ahead of time. You could fill in things like the track you're going to fly and the distances, how far is it, and stuff like that. You could fill in a lot of that ahead of time. We'll just go left to right today, but know that you might look at this ahead of time and do more. Okay, so true airspeed. For this, I'm just going to cheat, and I have looked in the pilot operating handbook at the cruise performance chart, and my true airspeed at 2,300 RPM and approximately 4,000 feet is going to be 100 knots true airspeed. So I'll punch that in there. On a written test question, they may give you a set number for some of the questions as well, and just say assume this is your true airspeed, and then you go from there. And calibrated airspeed. So this again comes back to the E6B. So this was the again the airspeed calibration window that we were using before. So I don't think I moved it. Let me confirm that things are still in the same spot. Ooh. Okay. 1, 2, 3.5, 3,500, and then 20 degrees. So yes, this is still lined up. So without moving the whiz wheel at all, we're already set up to do our airspeed corrections. So what we're doing is going from true airspeed. So we know the true airspeed because it came out of the book, and that's what it said in the book was true airspeed 100 knots. We're looking for calibrated airspeed. And it actually probably says, yeah, it says it down here in the instructions, true airspeed over calibrated airspeed, or in other words, true airspeed on the outer scale, calibrated airspeed on the inner scale. The other thing that I like to do is just kind of take a look around the wheel, and you'll see something like this, where it actually mentions, hey, true airspeed on the outer scale, calibrated airspeed on the inner scale. So if you see something like that, well, then you know that's how you should read it. So we know our true airspeed. True airspeed is 100 knots. So we just need to go and look at the calibrated airspeed that is across from that. So true airspeed outer scale, 100 knots. Looks like, so again, there's not a 100, but there is a 10. You have to kind of do the math in your head and figure that, or do the mental. Does that make sense? In your head and figure it out? But yeah, so 100 knots there seems to line up with about 93, right? So it's not 903. That wouldn't make sense. We're not going that fast. It's not 9.3 knots. That wouldn't make sense. So it has to be 93. So it is actually as written there, oddly enough. So that's the calibrated airspeed. So we'll put that into our nav log. 93. Indicated airspeed we will come back to later, just because I don't have the image ready to go. But that's going to come out of the POH. Let me... Oh, whatever. I'll see if I can find a real quick standby. I am looking for the page in the POH with the airspeed correction table. Scroll, scroll, scroll. Airspeed calibration. There we go. Didn't take that long. Okay, so we've got along the left side here, it says with the flaps up, which is what we are in cruise, with the flaps up, indicated airspeed on the top, calibrated airspeed on the bottom. We're starting with calibrated and going up to indicated in this example. So that's very important. You can't go top down because that would be doing the opposite of the operation that we want to do. Okay, so what I'm going to do is I'm going to look at approximately 90 knots. It's not exactly 93, so we're at 93 knots calibrated airspeed. We don't have 93 knots on the scale. It goes from 89 to 99. But what we have is, when we go from 89 knots calibrated airspeed, it goes up 1 knot to 90. When we go from 99 knots calibrated airspeed, it goes up 1 knot to 100. So if we're at 93 knots calibrated airspeed, it would go up 1 knot to 94. So that's our answer. That is our indicated airspeed, is 94 knots. So there we go. Indicated airspeed, 94. Bam. True track. Now we're back to the map. Take a look at the map. Okay. Here is where you pull out protractor again. I'm going to fold my map like a good pilot, fold it so that I can see the whole thing, everything that I need at once. Okay, so here's our route here, and with measuring track lines, it's helpful, or rather, it's slightly more accurate to measure from the middle of the track if you can. So that's what I'll do. I'll put the grommet that's in the center of my protractor. Around here. Yeah, so you can see there's actually a little hole in mine. This little grommet hole in the center, I'm going to put that in somewhere near the middle of my track line. That needs to line up perfectly on the track line, that grommet. The other thing is get north the right way up. So how I've got the map positioned, my north is this way actually. And so I'm going to put that. And then from there, it can be confusing exactly like, how do I position this thing? What you want to look for is, again, those latitude and longitude lines. Let me show you. So what you're going to do is look close to your track, and you can use the latitude, the horizontal lines, or you can use the vertical longitude lines. Doesn't really matter. And you're going to position the protractor so that it lines up parallel with these lines. You definitely have to have the grommet in the middle, needs to be perfectly centered on your line. But you're going to slide along the line to find a position where you can line up something in the background. Let me put the protractor back on here. You've got this grid pattern in the background of your protractor. So you don't have to have it perfectly on a longitude-latitude line, as long as it's parallel, as long as north is pointed north. So you could have a longitude line down this line, or you could have it, down this line, or it could even be on the edge of the protractor. As long as this is perfectly parallel with the longitude lines, that's what you want. And again, make sure north is actually pointed north, otherwise you'll be very confused. Okay, so that's what we're doing. Put that down on my map. It's going to be hard here to see that I have it lined up, but I'll try and demonstrate it in a sec. Okay, I don't know that you can bring this closer. I can't bring. Yeah, you might just have to trust me on this one. But there is a longitude line that runs right along here. Maybe if you're watching on a full iPad or a big computer screen, you might see this longitude line that's running right clear through this way. And it is lined up right on my protractor's grid here. So this longitude line here is what I'm referring to. And so it's lined up perfectly along that protractor grid line. And so I know that my protractor is pointed north. I'm also somewhere near the middle of the track. I'm not measuring from Chatsworth or from Waterloo. I'm somewhere near the middle. Now, knowing that I'm not flying north towards Chatsworth, I'm flying south towards Waterloo, I'm going to look down in this corner. One thing that can get you into trouble is you can flip the protractor upside down, and they've accounted for that in that there's a big number counting around this way, but I think they've got a little number underneath where if you got it upside down and you did all this work to perfectly position it, you can read the little number underneath and it counts up and around the other way. But anyway, I got it down the right way, and I'm reading out over here. And I think that's 160, it looks like. Yeah, it looks like it's bang on 160 degrees that I'm reading down here for my line. So that is my true track for this leg. 160. Bam. Okay. Wind speed and direction is next. So for that, I will look at not the METAR, and this is a very common thing that gets mixed up is, that's great, it shows me the wind speed and direction, but it's actually off by almost 90 degrees in today's case. I want to look down again at that FD, that upper level wind analysis thing here. Or analysis is a bad thing to say, because there is another one that actually they call it an upper level wind analysis. It's like a map. Sorry, the way to look at this is the FD upper level winds. That is what we're looking at. So out of Wyerton, I'll use the ones based out of Wyerton. I think they're ever so slightly closer to our route, but we do get closer to Toronto in the second half of the route. They are saying 350 at 5 knots. Actually, this is an interesting point. If we do look at the Toronto ones, both of them are headwinds, 350 versus 360 degrees. Wyerton is saying we're gonna have, or sorry, both of them are tailwinds. They're from behind us. They're coming from the north. This one says we have 5 knots ish of tailwind. This one says we have 13 knots ish of tailwind. It's actually more pessimistic to use Wyerton, so that's a better idea. I would use the more pessimistic tailwind number there. So that makes sense to me. So our wind, we'll put in 350 at 5. Great. Now it's asking me for my true heading. E6B. So for this one, I'll also do it on the iPad because it's easier for you guys to see. Okay, so I've got my wind side of the E6B now. So we were on the whiz wheel side. Now you're going to flip it over and you're on the wind side with the slidey slide on there. So we need to kind of take a look at the numbers that that we've got so far and kind of punch them into the wind side on the E6B here. Let me just peel a cat off of the cords. Kitty, do you want to say hi? Nope. Okay, so the best thing to do for this is read the directions. So I have my whiz wheel here with its directions. So mine, the wording might be slightly different, but the process should be the same for all of them. So mine says set wind direction opposite of the true index. So the true index, you can see here, is up on the top. So set the wind direction opposite the true index, and we know that the wind direction is 350 degrees. So that's what we'll do. We'll put 350 degrees opposite the true index. Okay, that was step 1. Step 2, mark a wind dot up from the grommet. So the grommet in the middle of the whiz wheel here. On mine, there's actually a literal hole there. You're gonna have it this, so there's a grommet there. You want to set a mark up from that grommet by the amount of the wind. So in this case, we've only got 5 knots of wind. So we're going to put the mark 5 knots up from the grommet. So the first things to do to make this simpler is to slide the slidey part so that 100 knots is under the grommet. And the reason being is you need to measure a number of knots up from 0, and so it's helpful to start from 100. I'm gonna line that up just good, and then like the instructions say, I'm gonna put my 5 knots of wind up from the grommet, and you would do just a little pencil mark or highlighter mark or something like that. Okay, so I've got my wind mark is set. That was step 2 on mine. And then step 3 says place true course under the true index. So again, the true index, this guy at the top. My true course, or true track, we called it on the navlog. True track is 160 degrees. So I've already got my mark on there. I'm going to slide this around 160. 160 under my true index. And then I go back to the instructions. Slide true airspeed under the wind dot. So it's really important to not put the true airspeed under the grommet. You put the true airspeed under the dot that we made. So as you'll remember, our true airspeed was 100 knots. So I'm going to put that under, in this case, I have this blue circle here. That's my wind dot that you would pencil into the E6B. So I got that on there. Go back to the instructions. Read ground speed under the grommet. Well, it looks like it's almost a due tailwind because we have now 105 knots of ground speed. That grommet there is halfway between the 100 and 110. So that's good. 105 knots ground speed. I will put that in the navlog. 105. That's good. Back to this. So read ground speed under the grommet. Read wind correction angle under the dot. And so that's using the scale in the background, how it has the graduations in the background, using that to determine how far off heading we will need to be. So in this case, let me just get so I can point, stand by. Okay, so we've got 0, and then we've got 10, and then it looks like there's probably 5 divisions, so let's confirm. So that'd be 0 degrees, 2 degrees, 4, 6, 8, and 10. So that's accurate. So it looks like our dot is maybe about, it's close to halfway. It's not quite halfway, but let's just, for the sake of argument, call it halfway. That'd be 1 degree. So we're 1 degree where we're going to have to crab for the wind. Looks like we're going to be crabbing to our left, potentially. We should go to the map, confirm that. So I'm going to align the camera kind of along the route we're going to fly. So taking off Owen Sound, Chatsworth, flying this way. The wind is from basically due north. It's maybe slightly northwest, but it's almost due north, so kind of due north this way. So that makes sense. We would have to turn the nose of the airplane to the left to compensate for that wind, which is slightly coming from our left. So that was accurate. So we are going to crab 1 degree to the left. Great. So we had a true track of 160, so we're going to be 159 for our true heading. Great. Okay, now let's go to the map again. The next thing on the nav log it's asking me for is the variation. It says VAR there. So we're already looking at this variation line, this 10 degrees west. How are we doing for time? Oh, we're departing in 53 minutes, by the way. So good luck to us. Okay, 10 degrees west was over there. And then we had 9 degrees west over there. It looks like we're a little closer to the 10 degrees west line, just barely closer to the 10 degrees west line. It also makes it just a little easier to do the math. So that's what I'll go with. So we need to add 10 degrees to our true heading. So we got 10 degrees west variation. I say add because west is best, east is least. We add west variation. So we're actually going to be 169 degrees for magnetic heading. Compass heading I will omit today because we haven't picked an airplane, but you would look at the compass correction card in the airplane, which would tell you 1 or 2 degrees or whatever to turn based on the heading. Very similar concept as what we were looking at with the airspeed calibration chart. It would say for north steer this other heading and that sort of thing. So you would have to look at, well, we're not exactly south or a little bit southeast, and you would kind of guesstimate in between how much error there is. So we will omit that. Ground speed 105. Distance is next. So let's come back to good old map. For this one, you'll grab your ICAO ruler, and for the ICAO ruler, it's very easy to read it wrong. And you might have some idea in your brain, oh, that sounds like it's about this many miles. And that might alert you if you measured it incorrectly. But also know that miles, like statute miles, normal miles to nautical miles, are only 15% off, so you might easily mix those two up. So on the ICAO ruler, it says statute miles on the top here, it says nautical miles on the bottom here. If it's your ruler and not one you're borrowing like me, you might consider either using a Sharpie or using black electrical tape and just taping out the scale that you don't use. So in my case, I don't use that statute mile scale. I don't want to mix it up. I need to use the nautical mile scale. And then it also mentions the outer scale versus the inner scale, and talking about the inner scale is 1 to 500,000 and the outer scale is 1 to 1,000,000. So in our case, we're going to want to use the inner scale on this one, so that we're using the 1 to 500,000 because that is our that is what our map is in. So that's funny though, because this must be an old ruler. Most of the newer ones. Oh yeah, this one says 1964 on it. That's interesting, because normally the outer scale is the 1 to 500,000. So I have a strange ruler. Your ruler probably isn't like mine. That's very interesting. So anyway, I will be using the inner scale for my ruler. Don't do what I'm doing if your ruler says outer scale is 1 to 500,000. The 1 to 500,000, this is why I read it, the 1 to 500,000 on the on there is what you're looking for. Okay, so I'm just going to go from Chatsworth to the destination. I get about 63, 64 miles there. That sounds pretty good. Okay, so I'm going to say 64 miles. Great. Gonna hide you guys. Okay, and then next it's asking for time, so we'll have to calculate that on the whiz wheel. So for this one, we know our speed and we know our distance. We're looking for the time. When you know the speed, it's always easier because you're going to put the arrow on the speed. That's the #1 priority. So I'm going to put the arrow to the speed. In this case, my ground speed is what I want, because I want to see how long is it going to take me to cover that much ground. So ground speed 105. I'm going to put the speed arrow on 105 there. Okay. So I got my speed arrow on 105. And I do know the distance is 64 miles. So I'm going to read the distance on the outer scale and then the time on the inner scale. So looking for 64. My 64 is up over here. I will show you a digital representation for clarity in a moment. So speed on 105, find 64 out over here. So I got 61, 2, 3, 4, 64 right there. And then I look at that across to here, and that looks like it's 36 and a half. These scales are kind of weird because this one, each mark is half of a minute. So we've got 35, and then you got 40 way over here. So it would be 35, 36, 7, 8, 9, 40. So you got to be careful with that. So again, I'm at 64 right here, would be 36 and a half minutes. Let's just call it 37 minutes for being conservative. So I will put that into my nav log. Yeah, what did I say? 37? Yeah, 37 minutes. Bam. Gallons per hour. So when you look at the cruise performance chart that I was referencing earlier, when we look at, we're going to approximate that we're pretty close to 4,000, kind of between 4,000 and 6,000 here. We're a little bit above standard temperature. We're going to be, about 100 knots here, kind of interpolating between these various different things. We're about 100 knots. We're going to be kind of 6.3 to 6.5, 6.3, 6.1. Let's go pessimistic. Let's say 6.5 gallons per hour for fuel burn there. So that's kind of the ranges that were in there. 6.5 I'm going to put down. Great. Fuel required for the trip. Well, for this one, or really, I guess we're just looking at the fuel required for that leg. So we're already at altitude. We're cruising from Chatsworth to the destination. So with that, we'll bring the E6B back into it. We know that we have 6.5 gallons per hour, and very similar to like a speed. It's like you have nautical miles per hour. That's knots. You have 6.5 gallons per hour. That's like a rate. The same sort of thing. So anytime you have a rate or a speed or something like that, you're going to put that under the arrow. So we're going to take the arrow, and I'm going to move the arrow of my whiz wheel around to 6.5, 6.5 there. So it's of course 65, but there is no 6.5. So you have to add the decimal place in your brain there. Okay, so we got 65 there. We know that we're going to fly this leg for about 37 minutes. So time is always on the inner scale. So 35 down there. We got 35. And then 40 is way over here. So we got, there's 10 graduations here. So it's 35, 36, 37 here. And then it'd be 8, 9, 40. So this is the mark that we want. So 37 minutes. We follow that across, and it should be 40 gallons. No, it's actually 4.0 gallons for that, which makes sense because we're only burning 6 gallons if it was a whole hour. So we're burning a little bit more than half of that. So that makes sense. So 4.0 gallons of fuel for this leg. 4.0. Bam. Okay. So that is the bulk of the planning part done, actually. We're going to look at filling in this leg here. And you don't have to get too fancy with this. We could go along and fill in every box, but think about what that really means. If we fill in every box here, are we going to come back later and say, oh, is my heading going to be this exact number to the number? Probably not. We'll calculate out a heading so we get a ballpark, but don't put too much weight into this leg, because a lot of it is just going to come straight out of the POH, actually. So let's just jump over to a POH excerpt here. So during this leg, we're going to be climbing, and so it's helpful to kind of start with referencing this. We're going to be climbing from approximately 1,000 feet. It's maybe about 40 feet off pressure altitude, but it's pretty close to 1,000 feet, up to 3,500. So somewhere in between this 3 and 4. So let's just call it 4,000 to take a look at these numbers over here. At 4,000, that would be from sea level to 4,000 would take 7 minutes, 1.5 gallons of fuel, and 9 nautical miles distance covered. We're not starting at 1,000. We're not actually going that high. So if we go between 3,000 and 4,000, because we'll be in between 3 and 4, it goes 5, 6, 7 minutes. So it seems like at 3,500, that number would actually be 6. 1.1 to 1.5. If we're somewhere in between there, well, maybe it's 1.3. From 7 to 9, well, maybe the distance traveled would actually be 8, right? So it would be 6, 1.3, and 8 would be our 3,500 line here. But also, like I say, we're not starting from sea level. We're starting from 1,000 feet above. So we then actually have to subtract this line here. And now I'm getting a lot of numbers in my brain, so I'm going to flip back and forth to our note paper. So we had 3,500 was 6 minutes. Let me clear out some stuff here. Okay, 3,500 was 6 minutes, and it was 1.3 gallons. And it was 8 nautical miles. Okay, so that's my notes, and then I want to subtract from that. I want to subtract my 1,000 foot line. So I'm going to subtract 2 minutes. So 6 minus 2, it should be about 4 minutes. And I'm going to say this is for our actual climb. Our actual climb will be about 4 minutes. Okay, and I'm going to go back to my 3,500 line. I'm going to subtract, on my 1,000 foot line, I'm going to subtract 0.3 gallons. So 0.3 minus 1.3. Oh, my cat is refreshing the page. Stand by. Cat is taking all of everything with him. Can't have that. Okay, so 1.3 gallons. We're not actually starting from sea level, so from sea level to 1,000 feet, there's 0.3 gallons that we're not actually using. We need to subtract 0.3, so 1.3 minus 0.3 would be 1.0 gallons. 1.0. Great. And we just need the distance, so we're not doing this 2 nautical miles. So we will subtract that. 8 minus 2 would be 6 nautical miles. Great. Okay, so the part I want to really analyze a little bit closer is this 6 nautical mile part. So let's jump over the map and see where we'll be after we've flown 6 miles worth of climb. So here's Owen Sound. Again, remember that my scales are probably backwards to yours if your ruler is within the last 2 decades of age. So after 6 nautical miles, we'll be right about here. So we'll have about 3 nautical miles to go to get to Chatsworth, right? So total distance from Owen Sound to Chatsworth seems to be maybe 9, maybe 10. Yeah, now I'm centered on the city. Yeah, it seems to be about 9 miles from Owen Sound to Chatsworth there. So when I fill that into the nav log, I'll just stick that in there so I don't forget. So 9 miles from Owen Sound to Chatsworth. We figure that 6 of that we're going to be climbing. So there's going to be another kind of 3 miles to fly after that. Let's just let me just think about that for a second. So it's going to be, I mean, it's close to the numbers that we have here. We're only talking about 3 miles worth of travel, which is probably about 2 minutes worth of actual flying time we're talking about that isn't included in what the POH just gave us. So let's just figure that out. I'll just ballpark that with the iPad. I won't put it into the navlog yet. But again, we have this is still set to 6.5 gallons an hour. If we went for 2 minutes, which is way over here, you might go, oh, that's going to be 2.1 gallons. It's probably 0.2 gallons, actually 0.22 gallons ish that we're going to burn in that time. So it's a very small amount of fuel burn there to fly those extra 2 minutes or so. So it's an amount. So why don't we just round that up? Let's just double our estimate. My estimate is, okay, we're going to burn 0.2 gallons in that extra 3 minutes. Let's call it 0.4, right? Again, this isn't necessarily how you would write a test question, but I find they don't ask you questions about in this much detail per se about like the set heading point, climb to this altitude and set heading point. But if you wanted to, you could say, okay, I got this 3 miles, calculate a whole new line on the navlog for that 3 mile leg. in the real world, I'm not going to do that. But you could do what we just did for the previous leg for that 3 miles if you wanted to be specific about it. But in my case, I'm not going to do that. I'm just going to say, okay, add an additional 0.4 of a gallon and add an additional 2 minutes to the numbers that we got. So let's do that. So another 4. So we started with 4. So it should be about 6 minutes to overhead Chatsworth. Add an additional 0.4 gallons. So I'm going to call it 1.4 gallons to overhead Chatsworth. And then that was to give us 9 nautical miles total. So that's what we'll put into our nav log. There's a little bit of guesstimating there, and that's okay because we've been pessimistic with the fuel part, which is really the part that matters. So, okay, 1.4. And then we figured 6 minutes. And then we figured, yeah, we put the 9 nautical miles in there already. So we're pretty good. Cool. Okay, the only other thing that we really need, I'm not going to worry too much about things like ground speed and that kind of thing because this is all an estimate based on the POH numbers anyway. What we should do, though, is at least get a heading to fly. That'll give us kind of our initial heading. We're going to be in the climb, so we're going to be visually navigating through these. So a lot of people put like just an arrow on these cells here to say like climbing. So there's no minimum altitude because we're in the climb the whole time. True airspeed, though, we can reference the POH here again. They don't give us a true airspeed, so I would say actually forget it. I'm not going to backwards calculate a true airspeed. We don't need to do that. But they gave us an indicated airspeed. We're going to be starting at 1,000 feet, going to 3,500. They're saying maybe 77 to 75 knots. So they're basically saying best rate of climb, right? So let's call it somewhere in the middle. 76 knots is the is what they're suggesting. You could also say, hey, maybe I don't want to do that. Maybe oh, I see the connection's dropping out. Okay, we're back there. You might say, okay, maybe I just want to climb at 80. That would be okay too, but the POH is suggesting maybe 76. Okay, I will look at, I see that we are dropping frames, but I think the audio is getting through okay. I will look at the heading for this. So in order to find the heading, I'm going to need to extend my line beyond Chatsworth so I can look at it with the protractor. So I've just done it lightly here with a pencil so that I can see it, but I'm not going to get distracted as I start flying. Okay, so I've lined my protractor up. Looks like it's about 196 degrees true track. 196. And we will punch the wind in there. We're probably going to have, you know, we are in the climb, so we're probably going to have something in between the surface winds and the 3,000-foot winds. So let's see what the surface winds are going to be. Surface winds, they're varying quite a lot. They're saying 260 at 3. Upper level winds, they're still saying 350 at 5. So it's all kind of northwesterly. Let's go somewhere in between those. Let's call it, for the sake of argument, let's call it 300 degrees. And let's be, or yeah, we can go halfway in between. Let's go 4 knots. So 300 degrees at 4 knots is my guesstimate of the average wind during the climb. Not an exact science there. This is all an estimate too because we're probably not going to fly this exact heading anyway, so I'm fine with being approximate. Okay, so we're going to come back to the good old E6B. Going to do one more of these wind corrections. So we had put in 300 for the wind. I'm going to put 300 under the true index. gonna get the instructions out so I don't do it backwards and do something silly. So I put the wind direction under the true index. I'm gonna make my wind dot, which I'm saying is 4 knots, up from the grommets. So to do that, I gotta line up the grommet. I'm gonna put my 4 knots wind dot up from the grommet, very similar to the 5 knot wind dot, and place the true course under the true index. So our true course or true track was 196 for this leg. 196. And then true airspeed under the slide true airspeed under the wind dot. Well, we don't have true airspeed, but we saw when we went from on the other leg, it went from 93 up to 100. We're not that high. It's probably not that much of an increase. So given that the true airspeed though is higher than the indicated airspeed, I feel safe to assume that the airplane's flying slower. I would just leave it at 76 again for this kind of approximation. Everything very rough on this leg because it's not even necessarily essential that you calculate all this out. It's going to be mostly visual flying. So anyway, I'm putting the 76 under my wind dot here. That looks pretty good. And it looks like I'm going to have a very slight tailwind. Maybe it's bumping me up to 77 knots ground speed. So that just also helps confirm that our time is probably pretty close. We're probably not far off on the time. And then it's also showing about a 3-degree heading change to the right. So that's the one that matters the most. And I'm measuring that just because our grommet is 1.5 cells towards this 10-degree line over here, right? So that'd be 2 degrees off. That'd be 4 degrees off. So we're 3 degrees there. So a 3-degree right heading adjustment. And so we were going 196. So we should be about 199. That's a true track. So we're going to add our variation in this area of the map. We are still in the 10-degree variation area. It's off in the top corner there, so I would still call that 10 degrees variation. So 10 west is best, east is least. I'm going to add that to get my magnetic, so it's going to be 209 degrees magnetic, and again we'll skip the compass. So really the 209 is what we did all that for, because that's what we're going to approximately be flying after takeoff to find Chatsworth. Don't need the gallons per hour there because we have a total gallons. So that's pretty much it. That's the navigation part done. And like I would say, I would put little indications in these cells to say like, no, this is a climb. I don't really need to calculate those ones. Great. So now we got to think about fuel. What do we got? We got 26 minutes before departure. We're doing pretty good. We might be a couple minutes late by the time we get to the airplane. Make sure it has enough gas in it. So okay, let's look at some of this fuel planning stuff. So I'm going to start by totaling up what we have so far. So we had 1.4 for the climb leg, and then we had 4 gallons en route. So the total en route, 5.4. Okay. Start, taxi, and run up. That is going to be based on, it's just straight out of the POH. I think it's right on this chart actually. 1.1 gallons we can put in there. One thing I realized is I didn't add the 10% for every 10 degrees Celsius above standard temperature. Let me do that, at least for the fuel, because I think that's important for the fuel, because I'm realizing I didn't do that now. So 10 degrees above standard temperature. Well, we are 1,000 feet above sea level. Standard temperature here is going to be 2 degrees less than standard temperature at sea level. So standard temperature at sea level, ICAO standard atmosphere, perfectly dry gas, and 29.92 is 15 degrees Celsius. So we are significantly higher than that. Let's see what Wyerton's reporting now. They're reporting 25. So we're about 10 degrees above standard temperature. Oh, isn't that a great test question? I love that. So we're 10 degrees above standard temperature, so we're going to add 10% to time, fuel, and distances. Again, you know, maybe if I had done that first, I would I would calculate that into our distance, and it might even be closer, but I'll just add the 10%. So 1.4, 10%, let's call it 1.5 fuel required. So then our total fuel, 5.5. I think all of this is being pessimistic, which is the way to be when you're calculating fuel, so I'm happy about that. Okay, so we got a total en route 5.5 gallons to get to the destination. That sounds cheap. That sounds low. We need to factor in that we got to get to the runway, and so this is, like I was saying, the 1.1 gallons of fuel for engine start, taxi, and takeoff. If you're writing a test question, they don't tend to say, here's your leg, calculate it, have fun, tell us the numbers at the end. They don't do that on the test question. They will have a test question on how to read this table. And then they will say, okay, here is your new, calculation. We want you to calculate this route. Assume it's going to add 5.6 gallons for start, taxi, takeoff, and climb to your set heading point. And you will just be required to calculate the leg beyond the set heading point. That's a typical test question, I find, because they don't want to, like, we just did so much complexity there, and you know, maybe I oversimplify this and then someone else does a little bit more granular, or maybe the opposite. They don't want to test you on everything all at once. They're going to ask you about they'll ask you to calculate basically one leg in similar detail to this, but they won't have you do that plus all the performance reading from the charts, plus doing picking a set heading point or anything like that. They definitely will be more specific so that you actually have a chance of achieving the same answer that they got. So don't be scared by this if you're about to write your test, like, oh my god, everything's so uncertain, because it won't be like that on the test. They will be very specific. These are the parameters you're to use for your test. Okay, so start, taxi, and run up. 1.1 gallons, I'm going to put that in there. Anticipated delays is an interesting one. We are going into Kitchener. We can anticipate delays going into Kitchener. That's just what it is. I would say I would at least anticipate a 20-minute delay going into Kitchener if you're going down there. I mean, we're going at 9 o'clock at night, so probably not that busy by the time we get there. But I could anticipate, as a general rule of thumb, at least 20 minutes going in there, even 30 going in there. Let's say 20 because we're going so late at night. But on a like during the day, we might anticipate a 30-minute delay. I'm realizing I didn't total the time, so I'll do that here as well. If you're math challenged like me, do this on a calculator. Don't try and tough it out and do it in your head and get the wrong answer and look silly like I would if I was to do that right now. 43 minutes total en route. Okay. We're assuming anticipated delays will probably stay at cruise, so that would be about 6.5 gallons per hour. And 20 minutes, 6.5 gallons an hour. I will show the alternate method of doing these calculations. 20 minutes divided by 60. That's 0.333333 of an hour. Yeah, add another 10 or 15 to finish the flight plan. Yeah. So this is funny too, because if we had called London Flight Service already, filed our flight plan, we might have to amend it by the time we get airborne. So a third of an hour here is our anticipated delays at 6.5 gallons an hour. I'm just going to multiply it. So 6.5 gallons per hour times 1/3 of an hour is 2.2 gallons, we'll call it. You can do the same thing on the whiz wheel. The equivalent on the whiz wheel is lining up the whiz arrow with the 6.5 and then reading the time on the inner scale, fuel used on the outer scale. but it's also possible to do those with a calculator. So, sorry, what was that? That was 2.2. Okay, so we got that in there. Total box 1, 2, and 3. There's box 1, 2, and 3. So we had 43 plus the anticipated delays of 20 minutes. So that would be 63. And then fuel used, we're going to total up these guys, equals 8.8 gallons there. Okay. Minimum legal reserve. Well, it's going to be just about nighttime by the time we get going. I guess night starts at approximately 9:48 tonight. So we should be able to do this during daytime still. Come on, it's only going to be 43 minutes en route. Let's just assume that we're day VFR flying this, and that we're not going to go 1 or 2 minutes into nighttime. We'll call our minimum legal reserve 30 minutes. But if it was a night flight, then if we were actually to go into night, then we would have to use 45 minutes. You know what? Let's do it. Let's make it real. Because if this was real, we wouldn't be pretending it's day. We would be saying, no, we're gonna be landing within probably 5 minutes of the end of evening civil twilight. We're gonna be landing within 5 minutes of nighttime. We probably should have the night reserve, even though legally, like, we should be down before nighttime. We probably ought to have that reserve. So let's do that. Okay, so 45 at 6.5 gallons an hour. I'll pull out my handy dandy calculator again. 45 minutes divided by 60. That's 0.75 of an hour times my 6.5 gallons an hour. 4.9 we'll call it. 4.9 gallons. Right. Okay. And I'm going to do a bit of a tangent for a minute. We know that we have, or sorry, there's this little arrow that's pulling our attention away to, well, this is how much we're gonna burn, likely. How much is in the airplane is kind of this little box down here. So we'll come back to this, but basically you would do all your planning using this, and you'd say, hey, the last guy that's using the airplane, this is how much fuel I want in the airplane. But then when you actually come to the airplane, you might have a different amount. So that's what this box is to say, okay, at startup, this was our actual amount of fuel that we had. This was the amount that we were anticipating having, or anticipating burning rather. And then what we can get at the end is how much fuel are we anticipating should be left in the tanks when we land at the destination, which is a nice number to know when you get to the destination and you want to dip the tanks and see how close your math was, right? So I'm just going to bring this 8.8 down in here. 8.8 gallons at 6 gallons per hour. Or sorry, 8.8 gallons at 6 pounds per gallon is what I'm calculating. I'm calculating the weight of the fuel is 52.8 pounds. So that would go into the fuel used line on your weight and balance. It's not the total fuel we'll carry. We'll have more than that, obviously. Okay, and then I'm going to bounce back up to where we were before. The subtotal fuel is basically the total of everything so far. So this box was already a total box. So 8.8 then plus my 4.9. So my total, including the trip and including reserve, is going to come to 13.7 here. Okay. I'm not going to get into too much detail right now, but if you open up the POH for the 172M that we're flying, on page 5-3, it talks about, not a 20%, I put the 20% in there, but it talks about expect variations due to various different things, such as possibly lies from Cessna back in 1976, possibly variations in engine and paint condition and yada yada. Expect up to a 10% increase in the expected fuel burn is what they're saying. Just to play it safe and add our own buffer to it, it's good to say, well, let's call it 20%, instead. And that's our kind of safety net to say, well, I'm not going to fly this flight with 8 gallons in the tanks. That's for darn sure. Okay, so I'm going to take my 13.7 times 0.2 for 20%. We'll call it 2.7 gallons of kind of additional, make sure that we're actually going to be good. So then we total all of that up. The fuel required, basically bare minimum fuel that we would require to safely complete the flight, 16.4 gallons. I also don't want to take off with 16.4 gallons because if we have more than a 20-minute delay, then we might be in some trouble. So basically that is like bare minimum. Anything above 16.4 we could do the flight, but more is better, of course, if you can fit it in your weight and balance. Then let's say, okay, we receive the airplane. They say, okay, you've got 25 gallons in the tanks. So here's where we can kind of analyze, well, what do we think about that? Do we think that is, if that's going to be safe or not? Well, we got, so first off, first thing to know is if you can carry more, right? So if maybe instead of, slightly different scenario, instead of it being, hey, I received the airplane, they said there's 25 in it, your weight and balance calculation determined 25 was the maximum you could carry. That's a better way to think about it, is carry as much as you can, right? So say 25 was the maximum that we could carry and still fit in weight and balance. So, because sometimes you do get those restrictions, you can't fly overweight, right? So I'll also just figure that out in pounds. That would be 150 pounds. Okay, so 150 pounds of fuel was what we calculated was absolute maximum, can't carry no more. So after we fly 8.8 gallons out of that, so 25 minus 8.8, we're going to be left with 16.2 gallons in the tanks. And again, this is not including our anticipated delays. This also isn't even including this variation. This is based on, you know, like the POH numbers. This is just based on what we think, based on the POH numbers that it's gonna probably burn there. And then we can calculate that out. You know, if we had 16.2 gallons at 6.5 gallons an hour, it'd be about 2.5 hours left in the tank. I think that's maybe a little more than I would estimate, and the reason being, again, is this kind of 20% variation. So I would maybe even abbreviate that and say, well, instead of saying at 6.5 gallons an hour, let's say 16.2. Let's call it more like maybe 8 gallons an hour. Like let's say 16.2. If we were flying at a very conservative 8 gallons an hour, well, then that's just about 2 hours. That sounds more reasonable to feel like, yeah, we could stay in the air for 2 hours without running out of gas after that. So that's like, if you fly for 2 hours, assume that you're running on fumes and falling into the sky after that point. But what that tells you is, if you've done your trip, if you've done your 43 minutes en route, and you get delayed, we've anticipated a delay of 20 minutes, but you could have a delay as much as not quite 2 hours, but maybe about an hour plus, you know, plus your minimum reserve, right? So this doesn't include reserve. This hasn't done the, you know, the reserve calculation hasn't done the 20 minutes, nothing. This is just purely how much flight time is left in the tanks after the anticipated legs that we're going to fly. So that's the oh, you know what? I just realized, oh, I said a stupid. That does include the delays, right? So it includes the delays because we totaled here, and then we brought that number down. So I said a stupid. No, so the this just doesn't include the reserve. So okay, that's good. So after the anticipated delays and the anticipated route, if we fly beyond 20 minutes of delay in this case, we only have 2 hours of fuel left in the tanks. That's better. It's good the anticipated delays are above because you want to anticipate that you are expecting at least 20 minutes. So, or you're expecting probably at 20 minutes. Okay, so that's kind of our, our calculation for fuel there. Ultimately, what I would say is this is the most interesting part, is this part down here, because what you're going to do is you're going to run through your fuel calculation and you're going to then go fly it, right? With 2 or 3 times as much fuel as you need, right? And then you're going to land at the destination and you're going to have a number in mind of, well, when I dip at the destination, I should have about 16 gallons. And so you'll dip at the destination and go, oh, I actually had blank. And then that can drive you to confirm, well, what do you think about the POH numbers? Are they high? Are they low? What do you think about, this 20% variation? Was it actually 20% off? Was it 10% off? Was it 3% off? So you can make your own determinations. You can then use this section here, this fuel analysis section, to test whether or not things are reliable. Say hi, kitty. sailing across. He wants to eat the cables. So yeah, that's what that box is all about. Okay, we got 9 minutes to departure. I'm sure we'll be exactly on time. No worries. What I want to do is scroll down. So if you print this off, it's good to print it double-sided, so you'll flip it back over. This is the display, or this is the page that's good to read when you're in flight. This summarized nav log, we're just going to copy stuff from up above. So it's lots of kind of flipping back and forth to get the stuff in here. So MEFs and MOCAs. And so basically this display here, or this section here, is an abbreviation of what's above. The idea is you're not going to want to read all this in flight. There's too much stuff on this page. But you'll go through column per column and copy the ones out that are in here. Just makes it a more pilot readable display when you're in flight. So heading, notice it doesn't say true or magnetic or any of that. You're going to use likely the compass heading that you calculated there. I didn't do that in this case, so I will just put my magnetic heading in because I don't have a compass card handy. Distances. Kitty is trying to eat all the cords. Classic cat move right there. Ground speeds. And times. So this says ETE for estimated time en route. So it's just the leg time, not an actual time that you'll get there or anything. Cool. Gotta kick the cat away from the cords. Okay. So this is a much easier section to read in flight. So we got our MEFs right there. So you're in flight, you're like, oh man, what's the MEF? There it is right there. Things like the weather's getting bad and the clouds are coming down. You'd want to know that kind of stuff, right? What the expected true airspeed, indicated airspeed, all that stuff, right? You go through and put in some different airports and frequencies. Let's do that. So we've got Owen Sound. There's lots of good info in the box here. So Owen Sound, airport ID, CYOS, elevation 1008 is also on the map there. 1008 on the bottom left corner there. And then we have ATIS, no tower frequency, no ground frequency, but we have an aerodrome traffic frequency, 123.0. Procedures, you could scribble in something about right-hand circuit, runway 36 if you wanted. We're pretty familiar with Owen Sound. Okay, continuing on. You could maybe put in something about Hanover. It's a little bit off of our route, but it's probably the closest major airport to our route other than the destination, obviously. So yeah, let's put in Hanover in there. It'd be a good kind of diversion option if the weather started to move in from the east side, especially. So CYHS, their elevation is 940 feet. No ATIS frequency, no tower frequency, no ground frequency for them. They have an aerodrome traffic frequency 122.8. And you could get into the procedures there as well. There's not a whole lot of room to fit in there, but maybe I would talk about, okay, it's a right downwind for runway 19 in there or something like that. I'm not anticipating landing there, so I probably wouldn't put too much thought into Hanover. Other than that, the big ticket one is going to be our destination here. There's not a whole lot written on the map in terms of frequencies or anything like that. We do have the elevation there, though. We have length of the longest runway is 7,000 feet. That's good to know. So let's start putting that in. Oops. So 1054 elevation. And then for the rest of this, we're going to have to move over to the Canada Flight Supplement. Okay, Canada Flight Supplement for Waterloo. There is some pages that I don't think are in these two. I think there's like, when you actually look in the Canada Flight Supplement, there is like a VFR procedures page that is worth reading as well. So don't take this as all the information you need to go into Waterloo, but it's most of it. So our main thing to fill into the nav log is our our frequencies here. So we got an ATIS 125.1. 5.1. I'll just copy in what I see here. I have a tower frequency on that page 126.0. And I have a ground frequency 121.8. And there's no aerodrome traffic frequency, but it might become a mandatory frequency at some points, and that would be 126.0. And we'll flip back over here. It has a note about sometimes it becomes a mandatory frequency there, and it says to talk to traffic. So it says MF, and then it says TFC for traffic on 126.0. So that's interesting because we know it has a tower. So for that, we have to look at more detail about the tower frequency. You can see it says from 12 Zulu to 04 Zulu. And let's look at what Zulu we're at now. We're getting close. By the time we get there, it's closer to 04, but probably still before 04 by the time we get there. We're only going to be about an hour en route. So if we depart in 2 minutes, then we will be probably only about 02 Zulu. So the tower should be open when we get there, but who knows, right? You would have to look at the NOTAMs. It's alerting me there's some NOTAMs to look at. We haven't looked at those yet. So who knows? They might have different hours with everything going on in the world right now. But yeah, that's what I would start at to look for in Waterloo. There's a whole lot of detail on, going to another airport, and just even something as simple as, how do I join the circuit? Right? We join the circuit on every flight. Well, how do I do it at this other airport? How do I do it at this other airport because it's controlled? Because maybe they have multiple runways. Waterloo has multiple runways, right? So how do I join the circuit if I'm going to the shorter runway or the longer runway and this and that? Waterloo is an interesting one because it's controlled, so they can kind of tell you however they want you to join the circuit, but there's a bit of a skill in anticipating what do we expect when we go down there based on things like the wind, right? As we're looking at the wind, 350 degrees. Well, they have a runway 32, so maybe they're using runway 32. Okay, how would we join the circuit from there? Maybe we would do a right downwind runway 32. Those are the sorts of things you want to plan ahead and you want to have considered ahead of time. Procedures, there's a whole lot of procedures here. You'll want to read up on those before you go. Not a lot of it that affects us as VFR, but they actually mention right in their right-hand circuits, runway 32 is standard. So that's good to know. Yeah, there's lots just to talk about that airport and how do we get in there and you know what's the order of operations. So for example, the controlled airport. First things first, before you talk to anyone, you'll want to tune to the ATIS. You want to figure out the ATIS information, the letter first, and then you'll call up tower with we have information Charlie, and then go in from there. So that's a big one. Let's look in terms of coming back to really what we've been planning here though is on the map. In terms of what we've been planning, we're going to need to call up the tower at some point going into Waterloo. And so I was talking about, well, you're probably going to maybe do that in this kind of area. You're in kind of this Fergus area, kind of between Fergus and Elmira over here. This kind of area, there's lots of good landmarks that you would be able to see. So that would probably be where I'd start thinking about calling them up. That's about 12 miles out. So it's maybe a little bit early. We only have to call about 5 minutes from the edge of the zone. Let's take a look here. Oh, okay, that's about 8 miles from the edge of the zone. So it's just over 5 minutes probably of flying time. So yeah, that seems pretty good. So that's probably what we would do. We would call them up over kind of the Fergus and Elmira, or sorry, Fergus and Elora area there. So that's good to kind of have planned ahead of time. Know those sorts of things. You could also analyze for things like, well, let's say I'm doing a bad job and I got off track and I don't realize that I've passed Fergus and Elmira and Elora and those places. What you could do is look at, well, there's the city of Kitchener-Waterloo. You could start thinking, okay, well, if I get to a point where maybe I'm starting to get close to this kind of corner of the city, or I look at that corner of the city and I look out like this, if I start to get into that area out over here, well, now I'm getting worried because if I got out over here and I haven't called anyone yet, then that's concerning. That's kind of a hard one. That's a hard landmark to maybe pick out. There's also maybe if I get the edge of the city abeam my airplane. If I get to that position and I haven't called anybody, I should be turning around because I can't continue any further because I need permission. Even St. Jacobs, that'd be even a better one, right? Just a couple miles out. If I see St. Jacobs out my right wing and if I pass St. Jacobs and I haven't talked to anybody, then I should be turning around and not continuing. So that's a good one that I like to add as well, kind of a safety net there. Cool. But then again, remember that it might be a mandatory frequency. It might not be controlled when we get there. The ATIS should tell you that. So then you would know, oh, it's a mandatory frequency. I don't need to talk to anyone in that case. Cool. Let's go back to the nav log. Last thing on the nav log, we're already in flight by this point. It's 3 minutes after our departure time. Last thing on the nav log I'll just mention is these en route checkpoints, and I'll just fill in one or two here for the sake of just kind of seeing what this is all about. So on the bottom here, these en route checkpoints. So we're gonna set heading over Chatsworth again, and when we're en route, I mean, this is only a 43-minute flight. It's not really a big deal in terms of having a precise, accurate ETA. But let's say that total en route wasn't 43 minutes. Let's say that was 2 hours and 43 minutes. Now it starts to matter. Fuel really starts to matter. Do I have enough fuel to get to the destination? Is it taking longer than it should? Is the key. Like, do I have more wind than anticipated and it's taking longer than it should? You should really be doing some en route recalculating of your ETA so that you know that you have enough fuel to make it to the destination. So for our route here, I think maybe this town of Durham here, it's kind of right next to these wind turbine farms. So you've got Chatsworth up in the top left corner. if we get kind of near the town of Durham, we are 17, 18 miles. Yeah, call it 17 miles along our route. So that's a good landmark to have. Oops. So when we get to Durham, we should be 17 miles into the leg, and the leg again was 64 miles. So that leaves us 47 miles remaining, right? So you put those in, and then now when you're in flight, you can use that to calculate. Okay, so I went 17 miles, write down the time when you're over Chatsworth, write down the time when you're over Durham, and then you can calculate, okay, what was the difference between the times? Okay, I went 17 miles and it took me 13 minutes. Okay, what does that mean my ground speed's going to be? Okay, that's my ground speed. What is my ETA now going to be with that 47 miles remaining, right? Let's do another one. So you can see how this part is actually pretty quick to just come up with distance to this point, distance to the destination. So let's keep going. Let's go a little bit further down. Let's look at maybe the town of Arthur's a pretty big town. Mount Forest. Mount Forest is pretty close to Durham, though. Not really any point in recalculating there. Yeah, let's take the town of Arthur. Town of Arthur right there. It's probably around the 2/3 point by the looks of it. Yeah, it's about 2/3. Okay, so I'll put that in there. Town of Arthur. Okay, and Arthur, I want to take the distance from Chatsworth to Arthur. From Chatsworth to Arthur, 40 miles. 40 miles so far. Okay, and then from Arthur to the, well, actually, I'll do this part mathematically. So 40 miles total trip, or sorry, total leg distance on this leg was 64. So then that should be 24 left. There we go. And same thing, you would take the difference time elapsed between Chatsworth and this point. That amount of time over 40 miles would give you a ground speed, and then take that ground speed with 24 miles remaining. It'll give you the time remaining, and you can calculate the ETA, the actual time on the clock from that. So, cool. I think we're ready. We can move to the airplane. We're only 8 minutes late. You can see how easy this is to take way more time than you think. Oh, the one thing I'll add, just because we're probably rushing to get on the phone with London Flight Service to file our flight plan so we can actually do this flight, we're anticipating time en route 43 minutes. One thing that we can do is, if we're anticipating a delay that it's likely going to happen, we can actually just go with this time and tell them that time, and then we won't have to change it when the delay happens like we expected. So total time en route, we'll call it 1.1 hours. So that's what we would, in this case, I would actually put that time in my flight plan, or I guess they do want it in hours and minutes. So yeah, we could call them, I don't know, if I was actually following this, I would maybe just say an hour and 10 minutes. I would actually tell them an hour and 10 minutes, and then the other thing to know is just you may have a stop. So in this case, we're just doing one leg. We're going to Kitchener, we're going to land there, we're going to shut down and do another plan or stay the night or whatever. If you're going to stop over there, say you're going to go and have lunch for 40 minutes and then come back, you want to include, if you're doing that all as part of one flight plan, you want to include all of that, including the stops and everything. They need the total time. Basically, they need from the moment that you lift off until you're going to call them on the phone to close your flight plan. That's the time that they care about for the flight plan. So yeah, we're good. We can file the flight plan. Not a 9 p.m. departure anymore, but maybe by the time we get in the airplane, start it up, maybe that's going to be 15 minutes, and then by the time we actually take off, give it another another 10 minutes or so. So we could say, you know, maybe 9:40 departure. So only a 40-minute delay in our departure. But you can see uh, how much time it could take. You know, I didn't do the performance calculations. You know, I'm kind of assuming probably do that the night before and then just confirm the numbers seem okay the morning of. You could see how that could suck down another 40 minutes on you, that sort of thing. Okay, so here we are, 9:10. What I want to do is show you start to finish how the technology can change your life, man. Um, but no, I think there's some benefits and there's some downsides to doing this on something like ForeFlight. Everybody loves you know, the simplicity of not having to do the 2 hours that we just did of calculating. But there's definitely some traps, and what you'll find is when you look at ForeFlight, the more you use ForeFlight, the more you'll see that it periodically pops up and says, by the way, all of this data is for advisory, not official. Like, be careful, don't use it for like true perfect navigation because it might not do what you expected to do, and this and that. And that's absolutely true. The old saying, garbage in, garbage out, right? If you put bad numbers into ForeFlight, you will get bad numbers out, and they will be very misleading. But what I wanted, so to start with that, these are things that you would have in there ahead of time. Things like the aircraft performance profile. So you put that in there once, and you spend a good few hours making sure everything's perfect for my airplane. And I'm not going to show it on the stream right now, but you tweak it based on, you know, my own, like I was saying with that chart. I'm going to go and I'm going to fly, and I'm going to analyze my fuel, and I'm going to see, okay, these are the actual numbers that I'm getting when I'm going and flying, and you know, compare that to the POH numbers. Maybe the POH numbers are a little bit optimistic. They tend to be a little bit optimistic. So compare that to what you're actually getting in the real airplane, and then put your best pessimistic guess into ForeFlight, basically. So that is what I've done. I've put a little bit more pessimistic. I think I got like maybe 90 knots instead of 100 knots and stuff like that, just because I want to be a little bit more pessimistic. So all those numbers, assuming that those numbers are accurate, I'm going to start with my altitude. I'm going to say 3,500, and I'm going to go Owen Sound. Hold on there, Owen Sound. Kitty is causing trouble. Stand by. Moving the cat. Kitty! Okay. Owen Sound we got in there. And again, Kitchener. Owen Sound and Kitchener. And then I'm just going to long press on my line, drag it over to Chatsworth. Bam. It doesn't have Chatsworth in there, but I'm just going to hit the lat long coordinates associated. So there's my route. One of the cool things I can do here... Oh my gosh, Kitty. Kitty! I was in trouble. One of the cool things I can do is I can select on the altitude. So you can see I've picked 3,500. Oh, it doesn't like my trigger speed. Okay. Oh, because I didn't pick my performance profile. Stand by. There we go. Okay, well, there's my performance profile. Don't blame me if it's not accurate. No warranty on that performance profile. Okay, so here we go. So I go to pick my altitude, and it's going to tell me, hey, look, here's some altitudes to fly, and here's the winds expected. So you can see ForeFlight knows what we kind of figured out from the upper level winds. There's less wind to go higher for us. There's less tailwind the higher we go. And it actually tells us, hey, at these different altitudes, these are the different fuel burns you're going to have at these various different altitudes. And I'm looking at that, I'm going, oh yeah, 3,500, 7.2. I could go a little lower, 3,000, save 0.2 gallons. That doesn't sound worth it. So yeah, 3,500, that sounds pretty good. I'll hang on to that. And then from there, so basically our route is loaded into ForeFlight, assuming all of our performance stuff is right. The other thing I can do is I can go to this profile view. Take a look at this. Initializing, loading. Here's kind of like airspeeds and airspaces and obstacles and stuff like that. We've got 3500 is indicated over here on the left side here, and we can kind of look along our route and what kind of airspaces, what kind of obstacles are we expecting at various different places. It's kind of neat. And if I trying to figure out how to drag this 3500 down, I'm not. Oh yeah, there we go. If I drag this down, it's going to start to warn me like, hey, you dum-dum, do you know that there's obstacles there and stuff? And it tries to guess like, here's your climbs and stuff like that. So it's helping you out trying to figure out obstacles and that sort of thing. I'm going to reset back to 3500. And then lastly, I've got a nav log in here, and it's gonna let's compare it to what numbers we got, because that'd be pretty interesting. It's gonna give us some estimates on kind of magnetic heading. So the second leg should be about 169 degrees magnetic there. Look in here, it's saying, it's small text, but it's saying 164. Pretty close. They maybe have some different winds or something like that in there. Yeah, it's pretty close. I'm surprised that it is that far off. It's a few degrees off from the numbers that we calculated, but yeah, it's pretty close. Another cool thing you can do in the grand finale of the whole shebang is I send this over to this flight screen. I open up the nav log button, and I send that to the printer. And in 6 minutes, we basically did 2 hours worth of work. So this is kind of more of a detailed nav log on pretty close to what we did. Now, the one thing that this doesn't really account for is it does have kind of an estimate of the fuel. Oh, that's interesting. That's only 1 gallon. See, garbage in, garbage out. Somehow I got 1 gallon for taxi fuel instead of 1.1. I don't know if that's displayed wrong or if that's inputted wrong. So, you know, stuff like that, it could trip you up a little bit. It's pretty similar to our 8.8 that we have over here, but it is off very slightly. So, yeah, I'm interested to know where that 0.8 of a gallon went for sure. So you gotta be careful with that. You gotta, like I say, garbage in, garbage out. Maybe my performance profile is not so hot. We also, well, the other thing too, since we really dug into the numbers and we were really careful with it, I know that we added at least 0.2, 0.3 of a gallon that we didn't actually need to. So we were being more pessimistic with these numbers, knowing how they're being calculated and going through very methodically. That's something you lose when you only do 6 minutes worth of planning. So you just got to be careful. Like I say, garbage in, garbage out. You got to be careful with what it is that you're actually planning and what it is that you're going through. But you can see the advantage of, if you set up your profiles to be even more pessimistic than I've done here, you can see how it's really going to save you a lot of time and gripe and and that sort of thing. And what I tell people is, don't take that time and then go and, you know, sip your coffee and you know, just relax. Take that extra time that you just gained to actually plan, and to actually, instead of doing paperwork for those 2 hours, spend that time to actually look at more weather information. We didn't look at any radar. We didn't look at any, you know, the GFAs or anything like that yet. Take time to look into that sort of thing. Take time to look into things like, hey, when I get to Kitchener, where am I going to go? Where do I even park? There's some FBOs on the field there. Take time to look into stuff like that. Take time to look at stuff like, hey, Google Earth has some really great information on kind of the layouts of things. And like in Kitchener, it's incredible. They got like this 3-dimensional whole shebang going on here. So you've got like the flight schools here, and then they've got like I think it's like flight line services over here, and then you can see like there's the old control tower, and they got the new control. There's the VOR that's decommissioned. Then you got the new control tower out here. You can really see like the layouts of the runways in a very intuitive way and everything. You can compare that to your publications from the airport layout. So this one here is the Nav Canada approved document. It is actually published by Nav Canada, but here's the actual, you know, taxiway layouts and stuff, so you can compare that kind of thing. So that's what I would encourage, you know, anyone that wants to get into the digital stuff for their real world flight planning. Use that additional time, and don't don't throw it away and sip a coffee, but do that for your real world. What am I going to do when I get to the destination? I think that makes a big difference. So cool. That is the stream, guys. And what do we got going on here? We got 7 people still in the stream. Thanks so much for sticking it out for 2 hours and 20 minutes. That's kind of some nav planning stuff for you. Great. And you know, you could see how, like I say, it can get away from you. The time can get away from you. It can take a little bit more than you would think. But I think that we generated a pretty good plan, and one that we could have printed off and fly it, and I think we would find the place anyway. So I'll leave it at that. No stream next week. We're actually gonna phase out the live streams here for the foreseeable future, as we kind of ramp back up into the real world in the airport kind of stuff. And so stop by sometime, you know, shoot us a message and stop by, I guess, because we're kind of appointment right now. And yeah, we're gonna be ramping up here, slow ramp up, but quick enough into some real world flight training. So come out, fly some airplanes, burn some gas, fly to Waterloo, do all kinds of cool stuff. Thanks again for everybody that tuned in. A lot of you guys were tuning in on a bunch of them, so that was great. And we shall see you in the air.